Thank you so much for inviting me. It's so nice for me to be here, so I'm very happy. I'm going to talk about some work that we did in the Math and Data group at the Center for Data Science at NYU with collaborators, in particular Zhendao Chen, who is here in the second row. So I'm going to talk about combinatorial optimization problems and on graphs, and I'm going to talk about graph neural networks. But it makes sense to start this talk saying that convolutional neural networks have achieved and surpassed the state of the art for image processing because they can exploit the invariances of the data. This is the second most famous picture in image processing. There's an article in The Atlantic about it, actually. So the features of images that we care about are that we can extract features from small patches that are the features are translation invariant, and they show up in several places of the image. So just like you have a very high dimensional space, but there's some low-dimensional structure that you can exploit. In this case, it's the structure of the grid where the image lives, and exploit that for profit and success in images. But what about other types of data? So what about molecules or natural language, manifolds, etc.? So what are the natural structures? And it seems that graphs are a nice structure because they are very general, and you can express data as graphs in general. And what are the relevant invariances in this case? In the case of the images, you have the invariance was given by the grid, and here the relevant invariance would be, and I'm going to justify this later, that when you're given a graph, the labels that you give to the nodes are not relevant necessarily, and they are not an intrinsic information for the graph. So maybe the representation that you want needs to be permutation invariant or equivariant with respect to the labels of your graph. And I'm going to describe what are natural neural network structures, and for instance, graph convolution networks and spectral GNNs, etc. And how can we analyze this? So graph neural networks is a very exploiting field these days. There is this GitHub repository that says these are the must-read papers on GNNs. And if you go to it, there are more than 300 papers that are must-read on GNNs. So I must say I haven't read them all. But there's, you have surveys, and there's many applications of these graph neural networks, and many forms, architectures of graph neural networks that one can use for computational chemistry, analyzing social networks, like identifying fake news, natural language processing, etc. And there are several types of graph neural networks. In particular, some graph neural networks that focus on designing filters in the spectral domain, or some graph neural networks that work with sending messages in the spatial domain. There are graph autoencoders, and there are graph neural networks that look at sequences of graphs and predict information out of that, like recurrent graph neural networks. And in this case, I'm just going to focus on the first two. The input for my neural network is going to be a graph that is going to be given by an adjacency matrix. And it may have some features for the nodes and some features for the edges. And the output of my neural network is going to be an embedding of my graph, or maybe a solution to an optimization problem. And the fundamental property that I care about is that if I apply a permutation on the labels of my graphs, then the output of my neural network is going to be invariant or equivariant with respect to that. So one application example, like example of an application that also is from Joan Bruna's group, is they apply these graph neural networks to this data coming from this IceCube neutrino observatory data. And I thought this was a very cool example to show you, because I don't know if you heard of it, but it's really, really cool. Like, I saw a YouTube video about it like last night. And what they do is they have, in the South Pole, they have an observatory for neutrinos that is below, like, so this says, like, this is the surface of the ice, and then this is like more than 1 kilometer below the surface of the ice, and then it goes 1 kilometer below, and they drill all these holes with hot water, and they put some sensors there, and the neutrinos are particles that have no charge, but they can go through these walls, and apparently this ice is very, very clear, so these neutrinos can travel like 100 meters below the surface, and they can hit these sensors. And so they want to identify like some sort of neutrinos that have high energy. I don't know much about that, but they have some signals that they want to separate the background noise from the action neutrino. And it looks like this, like the neutrino goes here, and it has like, well, like produces some information in the sensors, but not all the sensors. So you can think of this as a graph, and they model this problem as a graph, and they compare, as a graph neural network, they compare with the baseline methods like 3D convolutional neural networks, such as like the spatial information, and the physics baseline methods. For all these, they do it on simulated data, and they surpass the state of the art. And this paper like won a prize on something, so that's pretty nice. So anyway, so in this talk, I'm gonna give some motivation, so background on different types of graph neural networks, inspired on statistical physics maybe, and a natural way to compare the expressive power of these neural networks and some open problems. So the motivation that I wanted to give for defining these graph neural networks is the problem of clustering the stochastic block model, where you have some graph that you have two planted communities in this graph, and you draw an edge between two nodes in the same community with a probability, and across communities with a lower probability, and this is the stochastic block model. And then you want to identify the communities. If you see the adjacency matrix of the graph without, like, in the wrong order, then you don't see it. But then if you reorder the first nodes in the first community and the second nodes in the second community, then you see that this has like a low rank structure. And the expected value of this matrix is a constant, like a rank 2 matrix that you can identify. And so if you would take the spectral, like the second eigenvector, then that has the community structure. But if you have so in the expected value, then the second eigenvector gives you the community structure. But then if you have a sparse graph, then the spectra doesn't concentrate very well. So the Laplacian is not going to be useful for clustering, because the eigenvector that you want gets like hidden inside the bulk, and you don't find it. And there are other methods that succeed, like semi-definite programming. So that will tell you that maybe the spectral methods are not that useful in this setting. However, that's not true, because you can consider some spectral methods defined, like that actually Lenka came up with. So they realized that if you use this non-backtracking operator, then this spectral method coming from this non-backtracking operator reveals the clustering structure. And they also realized that you can write this Beth Hessian that is So this is a matrix that is indexed on the edges of your graph, and you can reduce it to the best Hessian that has the same dimension of your graph. That is a linear combination of the identity, the adjacency, and the degree for some specific parameters. And then if you look at the spectrum of this operator, you can recover the community structure from that. However, the reason why this works is a very, well, I don't know much about this, but it's not something that you can translate very easily to any data model. So if you have a different data model where you don't have so much independence, how can you derive a spectral method that works for your data? In particular, you don't have this like randomly generated data for this. So you may think that maybe for your data there exists a spectral method that will give you the classification structure that you want, but you may not be able to derive it, or maybe you don't have enough of such a good model. So something that you may want to do is, if you have supervised, if you have training data, you can think of it as, you can think of your problem as learning a good regularized spectral method, or a good general spectral method for your problem in your graph. So that's one way of thinking about these graph neural networks. So in particular, you can think of, well, my spectral method is going to be find the top eigenvector of a matrix. So I can do that using the power method. And then I can think of a neural network that will unroll this power method. Like if I do t steps of the power method, is multiplying the matrix M t times my vector. And then, so this is what I do. And then now the M is going to be a linear combination of some operators coming from my graph. And then there's going to be some coefficients that I don't know that I'm going to learn that are how I combine these operators coming from my graph. And this is like just what it would be to be the power method for a linear combination of these operators, right? But then what they do is they augment this model to say, well, actually, I can have a different, say, a different value for each of the layers, a different parameter at different layers. And also, you can think that actually, I'm not going to just learn a vector, but I'm going to learn an embedding to some like dimension greater than 1. So here, dt is the number of vectors that I'm considering at the layer t. And this is kind of like over-parameterizing my spectral method. Now my parameters are going to be the size n times, they're going to be size dt times dt plus 1, the number of vectors that I'm embedding at each layer. And then you can just use a nonlinearity. And then this is a way to construct one graph neural network as a generalized version of a spectral method. So something cool about this graph neural network is that you parameterize this graph neural network with some parameters that are independent to the size of the graph. So a priori, you can apply it to any graph that you want. So these graph neural networks can be applied to different sizes of graphs. In particular, you can train on one size of graphs and then test on another size of graphs. And that turns out to be useful. For instance, in the case of the neutrino example, all these graphs have different number of nodes. Something that Zendao and John Bruna did was they extended this model to also take the line graph into consideration. So they have graphs that are indexed on the edges. And also when you decide the set of operators of your graph that you see how you want to combine, you can also add some other graphs that encode information that you care about, like for instance the power graph that encodes the connectivity in t steps. And And it turns out that this, like using this kind of graphs allows you for way more expressivity. And something else that is useful for these models is that this model is equivariant with respect to permutations. So if I take permutation on the labels of my graph, then this permutation will happen here, and then my output will have the same relevant permutation. So then it would be equivariant.
Sorry.
Yes.
So you learn a spectral method basically that distinguishes graphs?
Yes.
You know exactly how many so is that a transformation of your spectrum basically that you learn?
It's a way. It's something similar to what was happening here. Like there is a combination of like a way of a Laplacian, like a generalized Laplacian, where a way to combine some operators from my graph that would give me a spectral method that will solve my problem.
So you kind of like learn linear algebraic properties of your adjacency meshes that are invariant against permutation.
And that will help you solve your specific problem, like a supervised way. In this case, it's supervised. Like, given your training data, what is the spectral method that allows me to recover this solution? So, in particular, in the case of the clustering the stochastic block model, which is what Zendao worked on, they show that the GNN performs as well as the belief propagation all the way to the information theoretic threshold empirically. They empirically show that, and they see that actually when they allow to have the line graph, they get much better performance, which is consistent with what you expect from the literature. And they have some theoretical results where they show that for like linear GNN, so with no linearity, and they can bound the loss value for like the local minima and the global minima by some quantity that depends on some concentration of some matrices. Okay, so this was in the supervised regime. So that can also be done in an unsupervised regime. For instance, for the max cut problem, where you are given a graph and you're trying to find a cut, a separation of the nodes in one set and another set, so that the number of edges between these two sets is maximized. And there are methods that you can use for this problem, like the classical SCP relaxation by Commons and Williamson, the extremal optimization algorithm by Bocher and Perkles, the graph neural networks, which are the ones that we are introducing here, and there may be a way to do it with a way to adapt the message passing algorithm that is asymptotically optimal for the Sherrington-Kirkpatrick Hamiltonian that Andrea did like last year, but I don't know how to adapt this algorithm or if it's even possible to implement it. But maybe that would be asymptotically optimal. And so we actually we train this in this graph neural network in an unsupervised way. So the loss function is going to be the cut value of the weighted cut, because you need this to be differentiable. So you cannot just take the cut, but you need to take the weighted cut. Or you can look at the expected value over a batch, like in a policy gradient setting. And you can compare the value that you obtain with the asymptotically optimal value, because there exists an explicit formulation for the asymptotically optimal value by Montanari and Dembo and Sen. And then we obtain that actually the graph neural network is comparable with the SDP and the extremal optimization, but the extremal optimization is the best method for this case. And the extremal optimization is a very simple, greedy algorithm that what it does is like it takes, it starts with a cut, and then it looks at different the different nodes that it can change from one set to the other one, and then they rank them according to how much the cost function would change, and then they just sample from a distribution with that in that order, and then they exchange nodes from one set to the other one with that. So it's quite puzzling why the extremal optimization performs so much better than anything else in this problem. But anyway, you can learn you can learn an algorithm for this problem in an unsupervised way here, and you can evaluate its performance because you know what is asymptotically optimal value. Okay, so another example, this is the last example that I wanted to talk about, is the quadratic assignment problem. So given two matrices, the quadratic assignment problem is an optimization problem in the space of permutations. And basically, you're looking for a permutation that maximizes this trace, which is actually equivalent to the graph matching problem. So finding a permutation that matches one graph to the other one and minimizes the discrepancy. And this, well, if you solve the graph matching problem, then you also solve graph isomorphism because is deciding whether this minimum is equal to 0 or not. And also, you can think of the traveling salesman problem as a particular case of graph matching because you want to match a graph that is a cycle with the graph that has the pairwise distances between all the points. Right? And you want to find the minimum discrepancy between these two graphs. And also, you can use that for measuring distances between metric spaces. And this problem is very hard. The graph neural network approach to this problem would be to train graph neural networks, like to train a graph neural network to find an embedding from your graph to some vector in Rn. And you use the same, you train it in a way that you find an embedding for these two graphs, and then you compute the outer product between these embeddings, and you round it to a permutation using Sinkhorn-Knapp algorithm or a linear program or whatever. And then the outer product of these two embeddings will be close to a permutation. That will be the permutation that you will send G1 to G2. And you can evaluate this graph neural network for some specific models. Like, for instance, if you have a random graph and then you apply a permutation and you add some noise, like a random regular graph or those Renyi graphs, and you can see that actually the graph neural network, in some cases, performs better than the semi-definite program or any spectral method or comparable. And also you can see how it performs with the traveling salesman problem. So far we discussed some graph neural network models and examples. Basically, the spectral GNN, and we applied it to classing the stochastic block model, the max cut problem, and quadratic assignment. So the next that I'm going to do is I'm going to talk about message passing neural networks and like linear invariant layers neural networks, and like how do you compare these classes of graph neural networks on some open problems. So the message passing neural network consists on a neural network where each node looks at their neighbors and they get messages from their neighbors with some values, and then they combine the values that they get from their neighbors with the values that they have with itself, and they send that information to their neighbors. So it's kind of like a message passing algorithm. And and there's some weights that are learnable. it also has this essential property that is invariant with respect to the permutations because you don't use labels for that. So there's this paper from ICLR 2019 that asks how powerful are graph neural networks, and they answer this question. This is Leskovic and Hekelga, and they answer this question by looking at the graph isomorphism problem. They say, well, I'm going to tell you how powerful are graph neural networks by looking at what non-isomorphic graphs these networks can distinguish. So in particular, they think of all the possible, like the family of possible graph neural networks as that are of this form, so parameterized by the parameters of the neural network. And they say, they ask, does there exist a neural network in this class that can distinguish these two non-isomorphic graphs? And if the answer is yes, then you win, and if the answer is no, then you lose. And they show that this message passing neural network can be as powerful as the Weiss-Ferrell-Lehmann test for testing graph isomorphism, which is a very simple test that I will tell you what it is. But actually, this WL test is also as powerful as the linear programming relaxation for this problem. So it's not very powerful. In particular, like the linear programming relaxation is just like when you in this optimization problem that we had before here, you replace X by a doubly stochastic matrix instead of saying that X is a permutation. And actually, in particular, that implies that you cannot distinguish between non-isomorphic regular graphs of the same degree, because then there is a non-integral assignment that says that has objective value 0. Yes?
I'm curious, these propagation areas, aren't they invariant to graph isomorphism?
Sorry?
But are these networks invariant to graph isomorphism?
Yes. So yes, that's the point, because if there exists a relabeling of the nodes that sends one graph to the other one, then the value of the function needs to be the same. So in particular, if both graphs are isomorphic, then all the functions in that class need to give you the same thing for both graphs, right? So this class of functions is functions that are permutation invariant.
So it means that you can't initialize them with random values, because that would make so the initial activations before the message passing starts has to be invariant to the
Yes, yeah, it needs to be, yeah. Yeah. So yeah, and in that case, you cannot distinguish them. So the idea for this Weiss-Ferrell-Lehmann test is you start assigning one color, like one label to every node of your graph, and then at each iteration, your label is going to be a hash between your previous label and the labels of your neighbors, and that's basically what this thing is doing. And you need to start with some label, like that's, yeah, and then you're distinguishing between labeled graphs. So in particular, if you don't want to have that nodes have different, like that nodes have different status, like then you will need to have that your original label is constant, right? Just like if you're looking at just the graph isomorphism problem, then your initialization need to be all the labels to be constant. And you can this algorithm, the Weiss-Ferrell-Lehmann test, can be generalized to look at k tuples of graphs of labels, and then you get the K Weisfeld-Liebman test that is more powerful than the one. This is just the one, so you just look at one neighbor, but then you can look at pairs of nodes for the two WL. And there's a GNN formulation based on this test that is as expressive as the Weisfeld-Liebman test. Okay. So that kind of tells you that the message passing neural networks are not very expressive in that sense, at least in the graph isomorphism sense. Another type of neural networks, graph neural networks that people have considered is this linear equivariant networks, and in particular, if you just consider all the linear functions that go from K tensors to R that are invariant, then you can think of it as a linear space, and that linear space is finite dimensional, and actually the dimension of that space does not depend on n. So you can think of it as if you have, say, just from matrices. So if you have the linear matrices, the linear functions that go from matrices to R, so that for all matrices, like f of phi applied to A is equal to f of A. So this is like acting by conjugation. Then you get that the dimension of all functions here is 2, because given given two elements that are off diagonal, then you can construct a matrix that is like 1 here and 0 everywhere else, and then there is a permutation that changes this 1 from here to here. So in particular, that would tell you that the function would need to be constant in the off-diagonal elements of your matrix, and the same thing would be like the diagonal, the same thing you can do on the diagonal. So in particular, the dimension of the linear functions from matrices to R that are invariant is 2, and then you can do the same thing with tensors, and the critical, so the dimension of the space is independent of the number of nodes that you have in your graph, but it grows doubly exponentially with the order of the tensor. In particular, this is a paper by Marron and Liebman, and the dimension of this space is B of K, with K is the Bell number, that is the number of partitions of a set in K sets. The number of partitions, And in particular, if you use these layers, like these linear maps, to construct invariant functions by just using a linear invariant map in each of these layers, in each of the layers of your neural network, then you get something like each of your layers are going to be a function that goes from a tensor to a vector, and you can construct these layers, these graph neural networks that are called invariant graph networks with these layers and activation functions. And this paper by Marron and Liebman and the paper by Kerem and Peire show that this composition of layers, like these graph neural networks, actually universally approximate the space of invariant functions, and they extend that to equivariant functions as well. But you need to go, in order to do that, like they use the Sohn-Weierstrass theorem. So in particular, the approximation rates are not known. But in order to do that, they need to go to much higher order tensors, and computationally it's not feasible to do it. So in practice, you can do 2 order 2, like with 2 tensors. But then if you go to 3 tensors, then the dimension of the space, maybe 3 you can do, but higher than that is not feasible. So theoretically, it's very interesting. So far, we have some families of invariant graph networks, like, for instance, the message passing neural networks seem not to be very expressive. These invariant graph networks with order k tensors universally approximate if k is arbitrarily large. So it seems like there's a gap between these two things. And the spectral GNNs, we don't know yet. But maybe we want to have a way to compare the expressive power of these classes of graph neural networks. And a way to do this is by looking at the graph isomorphism problem. That's something that has been established. And so we can say that a class of functions is discriminating for the graph isomorphism problem if given 2 non-isomorphic graphs, there exists a function in your class of invariant functions so that it has a different value for these 2 non-isomorphic graphs. So it's a function that solves the graph isomorphism. Like your class of functions can solve the graph isomorphism problem. And in particular, if you solve the graph isomorphism problem, then of course, okay, so if you can universally approximate the space of invariant functions, then of course you can solve the graph isomorphism problem. And also, if you can solve the graph isomorphism problem, you can construct a new, like if you have a class of functions that can solve the graph isomorphism problem, then you can construct a neural network that can universally approximate all invariant functions. So in particular, looking at universal approximation and looking to solving graph isomorphism is kind of equivalent in a sense. And we can use this tool to look at different classes of graph neural networks and compare their expressive power. And that's something that we did. So in particular, so if you have the spectral GNN that we had at the beginning, then the more operators that you add to your space of M that we had earlier, like what operators are combined, then the more expressive you are. In particular, adding these power graphs that we had here actually makes it very expressive because you can construct examples of graphs that cannot be distinguished with these, but then once that you add these power graphs, then you can distinguish. In particular, these graphs that are regular with the same degree, but they are not isomorphic, because you can look at like the topology of the k-hops neighborhoods, and then that would distinguish it in that particular case. And also the message passing. So here we have the message passing. Neural networks are as powerful as the linear program, which is equivalent to the 1WL and equivalent to this graph isomorphism network by Leskovich. And then you can think of a semi-definite program that looks at the graph isomorphism problem, and then that would be more expressive in the sense that it will distinguish more graphs than the linear program. You can also look at the sum of squares hierarchy, but I don't know how that compares with the rest of the neural networks. But anyway, just as a way of comparison, the expressivity of this, yeah.
But how do you deal with the fact that a hypothesis class could solve graph isomorphism but needs exponentially many resources or something like that?
Yeah, so here you are restrictive. So here is like these linear layers, but here you're only using 2 tensors. Okay. Sure, like if you make this k goes to infinity, then you have the whole thing. Like probably like if you make the SOS hierarchy and you make that go to infinity, then you have the whole thing. Yeah, okay. I don't know. Yeah.
Because it would be interesting how fast these models are probably.
Mm-hmm. Yeah. Mm-hmm. Yeah, I think that's a very nice question. Yeah. So in particular, when this order 2 G-invariant networks cannot distinguish between regular graphs either, but then we extended the model to consider these ring graph neural networks. So I'll show you what it is. And those ring graph neural networks succeed in distinguishing these graphs. So you can just add like a very small thing that doesn't change much your computational requirement, but makes your class more expressive. And the way we consider the ring neural network is by consider these linear invariant networks on matrices. So the dimension of that space is 15. So they're equivariant. And then we allow multiplication of the output of these two layers. And then so you have these linear maps from matrices to matrices, and also you can take two and then multiply them. And that gives you more expressive power that you can actually say how much it is, or at least like give some lower bounds. And you can also add, for instance, we added some form of spectral method to this, but then that's actually not necessary. Like you can look at the eigenvalue of your matrix if you want in your loss function. Okay, so yes. Okay, so I'm almost done. So for open problems, I will say that an interesting was actually there's a paper by Maron and Lippmann in some NeurEPS workshop that states a list of open problems for graph neural networks. In particular, the overarching problem, I guess, is how do you find a scalable graph neural network that is both invariant, of course, and expressive, and how do you connect the architecture or the depth with the classes of graphs that they can separate. In particular, they ask whether the KIGNNs, like these invariant networks, can implement a KWL test. That's an open problem. And of course, open problem is what is the optimization landscape in these graph neural networks. And this, so this current analysis of these graph neural networks is restricted to have stronger assumptions than the actual model. And something else that is connected to these graph neural network models for physics is to extend these the graph neural networks for symmetric functions to the antisymmetric case, which is useful for some specific problems in physics. So what are nice architectures that would express antisymmetric functions instead of symmetric? And there are many challenges there because of instability of the determinant, etc. And something that I'm very interested in right now is to understand the connection of these graph neural networks with sum of squares, because okay, so there is this result for sum of squares that show that if you have for certain classes of problems, if you have a sum of squares refutation, then that implies that there exists a spectral method. And that spectral method is actually not given explicitly, but it's a spectral method on the size that depends on the degree of your sum of squares. And then not only the question that, okay, can you find this spectral method that has like a weird shape with a graph neural network, but also the fact that we believe that these spectral methods that they construct here, therefore deciding between a model on a graph and a planted model. Say this graph has a planted spike, or it's just like a model from, or this tensor has a planted spike, or it's just a random tensor. And the fact that the question comes from these graphs has this permutation invariance issue also there. So it seems like the spectral method that they obtain in their proof should actually be permutation invariant as well. So in particular, that tells you something about what is the dimension of the search space of your spectral method. And then it should be much lower than expected. So maybe the complexity of the problem is much lower than expected. And yeah, and that's something that I'm interested in. So yeah, this is it. Thank you very much.